Okay, so I want to talk to you about the three types of the units in the metric system: length, mass, and volume. Okay, so as we know, English versus metric, we've talked a lot about this. Metric's a lot easier because it goes by values of 10. Make sure you go through this slideshow so you can see some of the different conversions. A mile or a kilometer just gives you some comparisons to English systems so that you're familiar with that. Tells you how much an inch is worth. These things are not going to be on your test coming up, but it's kind of nice to see, since we still use the English system, what that equates to in metric system. The things that we want you to know, that kilometers is 1,000 meters, right? Kilo means 1,000. Centimeters means 100th. That's why it takes 100 centimeters to equal a meter. And milli means 1,000. That's why it takes 1,000 millimeters to equal 1 meter. So which is larger, 1 meter or 1.105 centimeters? So we've been talking a bit about this, and using the ladder method, right? So in order to do this, you have to convert one of the units. So you can convert meters to centimeters or centimeters to meters. Let's just start here at meters. I know that a meter, okay, is that it takes 100 centimeters to equal a meter. That means centimeters is 2 places to the right of meter. So if my decimal's here, I'm moving 2 places to the right, rewriting my decimal. I know that it's 100 centimeters. So 105 centimeters is greater than 100 centimeters, therefore 105 centimeters is greater. Okay? 4 kilometers to 4,400 meters. If I look here, a kilometer is 1,000 meters, so I'm going to convert kilometers to meters. 4 times 1,000 is 4,000, which is less than 4,400 meters. Again, if I was using the ladder method and I had kilometers and my decimal was here, I'd move 1, 2, 3 places to the right, and I would fill in those places with 3 zeros, and so I would get 4,000 is another way to look at it, right? So again, 4,400 meters is greater. 12 centimeters or 102 millimeters. Okay, so centi is 100th, milli is 1,000th. That means milli is 10 times smaller, because 10 times 100 would be 1,000. Okay, so it's 10 times smaller. It's 1 place to the right. So if my decimal point's here on 12, I move 1 place to the right. 12 centimeters is 120 millimeters, right? And 120 is greater than 102. And the last one, 1,200 millimeters or meter. So my decimal point's here. I'm going to convert from millimeters to meter this time. Milli means 1,000. There's 1,000 millimeters in a meter. So I'm going, my decimal point's here because it's a whole number. It's always here when it's not written, to the right of the number. And I'm going to move 3 places to the left. 1, 2, 3 places, and that gives you 1.2 meters. So 1,200 millimeters is 1.2 meters, which is greater than a meter. Okay? So this is kind of the markings on the ruler. We see that there are 10 millimeters in a centimeter, right? It's 10 units smaller. Okay? So in this case, I'm not going to go over all these. The length of the line is 1.0 centimeters. Length of the line in millimeter is 10 millimeters. I count those little lines. What's the length of the line to the nearest centimeter? I've got 1, 2, 1, 2, 3, 4, 5. The longer line in the middle between the 2 centimeters is 5 millimeters. So it's 2.5, 2.6, 2.7, 2.8 centimeters. And if I wanted to round that to the nearest centimeter, I look at the tenths column, right? 2.8. 8 is 5 or greater. So it would become 3.0 centimeters if I was rounding that, okay, if there was no decimal. Okay? And I think that's all I have on metric length. Let's look at mass. Okay, mass is the amount of matter in an object. Okay, we measure that in grams. or kilograms. The closest equivalent we have in English measurement is pounds, although pounds doesn't measure mass, pounds measures weight, right? So what's the difference between mass and weight? Well, mass is the amount of matter in an object, so it's the amount of molecules, right? Molecules and atoms that's inside something. So I have a tree pouch in front of me filled with little kibble food for Pear, okay, for the dog, okay, the guide dog we have, all right? So I can fill this pouch with kibble, and I can keep filling it with more kibble. What I'm doing is adding mass to this, right? I'm adding the molecules, I'm adding the stuff in it. If I don't ever take anything out of this, the mass doesn't change. The amount of matter in it never changes. Doesn't matter if I'm here, doesn't matter if I'm on the moon. However, if I were to weigh this on this Earth on a scale, on a spring scale, gravity would pull this bag down to the ground, right? And it would press on that scale and it would give me a weight. My weight would be in pounds, okay? If I went to the moon, because gravity is less, that pulling on that scale would be much less there. So my weight would change. However, the amount of kibble that's in the bag, the amount of stuff, the amount of matter did not change because I didn't take anything out, okay? So that's mass, the amount of matter in the object. So when we talk about measuring mass, I want to skip through here a minute, we use a triple beam balance. And the reason a triple beam balance is different from your bathroom spring scale is because this balances the weight, whereas your spring scale just pulls you down on top of it because of gravity pulling on you. But when I use a spring scale, a balance like this, I'm taking these 3 bars, I didn't want to go back there. I'm taking these 3 bars right here, okay? And they're on this side of the balance, and I'm trying to balance them with this white line, get them nice and even to an unknown quantity on this pan. If I get them to balance out, I'm negating gravity, right? Like being on a seesaw. If you are in the air and your friend's in the air and you're balanced and no one's hitting the ground, then you don't have the force of gravity acting on you. It means that the person on one side is counteracting whatever's on the other side. You are now at an equal force on gravity and you won't move. That's what you're trying to achieve on this scale. You're trying to get known quantities of mass on one side and measuring that against an unknown quantity on the other side. Okay? And when you get this to balance, you know that this known quantity is equal to that quantity. So whatever you read over here is equal to the mass over there, right? Okay. The last thing I want to cover is volume. I want to take a quick look at volume. And so we have English measurements for volume, gallons, ounces, but in metric we like to use the liters and milliliters, okay? And you can look at this at some of the different, a gallon equals 3.79 liters, a quart equals 0.946 liters. Again, because fluids and ounces aren't based on units of 10, the measurements are kind of all uneven. This is a cool graphic here because it shows you what volume is. Volume is the amount of matter in an object. When you have a regularly shaped object, that means it has sides you can measure. Like I can measure and count this as being 10 centimeters and 10 centimeters and 10 centimeters. When I have that, I have my length, my width, my height. And the way you can always find the dimensions on an object is by picking a corner. Let's pick this corner down here. And I can go left, right, and my third dimension here. You might say, wait a second, there's no measurement there. Yes, there is. The measurement's right here, okay? And so this measurement is the same as this measurement right here, okay? So that's kind of important to know. So length, width, and height can give you the volume of a regular object, okay? We can measure volume of things that are irregular or liquids using graduated cylinders, right? And you always read the bottom of the meniscus because there's a lot of space and air here, and there's more of the fluid by measuring the bottom. It's more accurate than measuring the top, because you would be measuring all of this extra space as volume, which is not true. That's not part of the volume of this substance that's down here. Okay? The last thing I want to show you is water displacement. We can also use liquids in graduated cylinders to measure the volume of things that do not have regular shapes. For instance, this rock can't be measured with sides. So what do? Well, if I know a known quantity of liquid like this water, and I measure it at 200 milliliters, and I drop a rock in there, and now the height of the water rises to 20, 40, 60, 260 milliliters, well, what's the volume of the rock? Yes? 60 milliliters. Very good. You take the final volume, you subtract it from the initial volume, and whatever that is the volume of that object you dropped into the liquid. Okay? Any questions on any of those things involving mass, length, or volume? Okay. I want to go ahead and talk about the last thing then. Okay, I want to talk about density. And density is a ratio. It equals mass divided by volume. Okay? It's not a known quantity, it's a ratio. It's a comparison of two other known quantities. Let's go back to this pouch filled with kibble. It has a volume, it takes up a certain amount of space, and it has mass in it. We're going to, again, pretend this kibble, these little dog food pieces, these little round dog food pieces are the atoms or molecules inside this bag. Okay? So right now it has a mass to volume ratio. I could put this on a tripping balance and measure the mass. I could try to measure the dimensions and get the volume. And it's got a certain density, because any number, let's pick a number. Let's take the number 20. Let's say it has a mass of 20 grams. Okay? And let's say that it has a volume of 5, we'll do centimeters cubed. Remember, a centimeter cubed is equal to a milliliter, excuse me. So those are interchangeable units, depending if you have a solid, regularly shaped object or you have a liquid. Okay? So what's the answer here? What's my density? I have 20 over 5. What's my density? What's 20 divided by 5?
4.
4. I have 4, and don't forget your units, grams per centimeter cubed.
Yeah.
Now, let's say this bag of kibble, I take more kibble, more matter, more stuff, and I stuff it into this bag. And let's say I stuff so much into this bag that I increased my mass, because I put more matter into it, to 100 grams. I still have the same volume at 5 centimeters cubed. What is my new density because I stuffed more matter into this object? What's 100 divided by 5? 20? No, 20.
20 grams.
20 grams per centimeter cubed. So this is why you have things like, if I had 2 cubes made of different materials, one was styrofoam and one was lead, the lead would sink to the bottom of a glass of water when the styrofoam would float. And the reason that is because the molecules or mass in the styrofoam is spread out more. We don't have as much mass packed into that space. So its density becomes less than 1, the ratio. Whereas lead is very dense. We've packed a lot of stuff into that small space, and it gets very, very dense. Okay? Any questions on these units?